Hey guys, welcome back to the channel. In this video, we'll be talking about the Convex Hull Trick, which is basically a dynamic programming optimization. So we're going to be looking at the problem Frog 3 from the AtCoder DP Contest. And so the problem is basically that we have n stones arranged in ascending order, and to jump from some stone I to some stone j, where j is greater than I, we incur a total cost of h of j minus h of I whole square plus c, where c is some constant. And now we have to find the minimum cost to reach the last stone, which is stone n. So the n square solution, which is actually slow for this problem, is actually standard dynamic programming, which is just so dp of j is the minimum of itself, or dp of I plus h of j minus h of I squared plus c. Now we do this for all j and for all I less than j. And since this is n square and n is pretty large, this will TLE. So now let's rewrite this recurrence. So dp of I plus, let's open this up. It becomes h of j square minus 2h of j into h of I plus h of I square plus c. And let's move the terms around a bit. So this should be h of I plus the fixed cost c and h of j squared. So we've moved our terms around now. And for some j, now what are the things that don't change? So for if you're at some j, while taking our min, this will never change, this is constant. This never changes because the height remains constant. And this part also never changes. So let's keep these two separate. And let's keep this separate and this separate. Now, if you look at the equation of a straight line, y is equal to mx plus c, you can actually see that this recurrence we have is actually y is equal to mx plus c. How is that? Well, we can say that h of j over here is our x value, and minus 2 into h of I is our slope, which is m. H of I square plus dp of I is the constant y-intercept, which is c. And these two we can just add in the end because they don't really matter. Now, this is important because this brings us to the convex hull optimization. Let's see what the convex hull trick is now. So the convex hull trick is basically a dynamic programming speed up, and I just showed you how you could rewrite that recurrence in the form of the equation of a straight line. Now let's see what we can do if we have a bunch of these straight lines. So you can see for some range of x values, some line will always give you the best y value. Let's say for every x value, we want to find the maximum y value we can get. So if you look at this range of x values, considering we have these three lines till the end, from this point, for every query, if we query some x value, we'll get some y value corresponding to this line, which we can see is the maximum for any line lying in this area. Similarly, from this point to this point, we can see that if we want to find the maximum y value, the red line gives us the optimal answer. And from that point onwards, all the way to the end, this white line gives us the best answer. Now, why is this useful? This is useful because we can simply maintain some data structure that uses those DP terms we gave it to efficiently find the minimum or maximum value. Okay, so let's consider three cases. The first one is when all of the slopes are monotonic and all the query values are monotonic. This means that all the slopes are either decreasing or increasing, and all the query values are either all increasing or decreasing. Second case is when only the slopes are monotonic. And the third case is when we don't have anything special. So as you saw, each line has some range of x values that it gives the optimal answer for. Now if you look at this part, it forms a convex hull, and that's where the name comes from. Okay, so what are these cases? Well, when our slopes and query values are monotonic, that means that every slope we add to a data structure. For this, let's look at this particular problem. Let's say we have a line like this. Now the next line we add will always be tilted like this. It will have a more negative slope. And when we always know that this is true, we know that every new line is a possible candidate to give us the better answer from some x onwards. Now what that means is, suppose we have lines like this, and now we add another line which goes like this. This is the first line. The second line that we added, and the third one. These lines will be straight. The drawing isn't that good, but whatever. And in this problem, we have to query for the minimum. So we have the first line, which is just going to be there because we didn't have anything better. Now, when we add the second line, we can, since we're querying for the minimum, we can see that the second line from this value of x gives us a better minimum than the first line. So what we do is now we just save this portion as the optimal hull. And now the third line we added, again, it gives us a better answer from this x value onwards. So again, this is optimal. Okay, this particular problem, frog 3, it lies in the first case where our query values are all monotonic. Basically, our heights are given in increasing order. So now what we can do is, let's say we're querying for some h of j, okay? Since we know that h of j plus 1 will be greater than h of j, we start looking at our data structure from the back. At each line, we also store the point at which it starts becoming optimal, because this line isn't always optimal. For any portion before this, this is the optimal line. So the initial line, it starts becoming from x coordinate 0, but for the second line, we have to find the time at which it starts becoming useful. And that is the time when it intersects with the line before it. So let's take two equations. Y and x are the same because when they intersect, the point is the same. And let's equate this. Okay. So now this we can find out the point at which some line becomes useful using this formula. So now we have two types of operations we want to do. We want to add a new line, and we want to query. That is basically find some line which gives us the best value for our x query. So let's look at what we do when we need to add a line. So we maintain some data structure like a double-ended queue, which is called a deck, and we store all our x values in increasing order. What that means is we maintain pairs of lines and the x value at which they become useful. And since our query values, the heights are increasing order, every time we want to query, we look at the back of this until our query value, which is h of j, is greater than or equal to the optimal x value. We keep on removing the lines from the front of this data structure, and we can remove them because we know that our next query will be greater than this. So we won't be removing any line that we actually need. But when we have the second case, when only the slopes are monotonic and the query values aren't monotonic, we actually need all these lines. So we can't remove any line. But what we can do to find the optimal line for some x is basically binary search. Since all of these x are in increasing order, we just need to binary search to find the first x which is smaller than or equal to our query value, which will, so that's q.log n. Log n operations per query. Okay, now this problem will fall under the first case where our query values are monotonic. So let's not worry about the second case for now. We'll take a look at the third case a bit later. Right. So now when I have to add a line, what do I do? Well, because I know my slopes are monotonic, and since we want the minimum, and each new line is a possible candidate to give us a better minimum from some x onwards, we basically start looking at the back of this data structure. We check if the new line we want to add and the last line in our data structure, we find the intersection point, and we check if that's less than or equal to the line we already have and its intersection with the line before it. So let's say we have n minus 1, we have these lines in the data structure, and we want to add a new line. We want to add this particular line. Now, okay, so what do we do to check if this line will actually be useful or not? Well, so let's say this is the last line and this is the second last line. We know their point of intersection, which is this. And now, what we basically need to check is the new line more useful than our last line or not? Now, the only case when it will be more useful is when the intersection of the new line with the last line is before the point this last line intersects with the second last line. So the new intersection is something like, let's say this. You can see that from this value of x onwards, the last line actually becomes useless, and before that this line was already, and before this point this line was already useless because we had the second last line. So now what we do is we remove the last line from our data structure and continue checking this with all the lines. Now when this case is false, which means we have something like this, we can clearly see that this last line is giving us the minimum value up till this point. After that the green line becomes better. So now we just add the green line to the back of our data structure with this new intersection point telling us the x value from which this line starts becoming useful, and our final data structure looks something like this. Okay, so this is how you add a new line. Now what do you do when you want to query for some line? So like I explained earlier, since all these lines have the point at which they become useful, we've kept it in increasing order. And since our query values are monotonic, we just look at the back of this data structure and keep on removing lines until we find the x value we're looking for. Okay, so that's it for the first two cases. Now what about the third case? Well, we clearly can't maintain this sort of deck structure when we don't have any special property, like the slopes aren't monotonic and neither are our query values. So in that case, we use some dynamic data structure which can handle different slopes and different query values. And a really easy way to do that is with the Chao tree. It's kind of a segment tree, but it's a bit more advanced and we don't need it for this problem, so I'm not going to go into it, but I'll leave some links down in the description for you to read more on it. So now let's actually look at some code to understand what I mean here. So I've basically made this struct in C++. This one stores information about a line, which is the slope, the y-intercept. This is just a constructor. This val function, it just returns the y value if we give it some x value for this particular line. Now this intersect function, this is basically what I showed you over here. It's the same formula. We basically find when two lines intercept, and we take their ceiling. Since our x are in increasing order, we should take their ceiling, which is just what this trick does over here. So this function finds the point at which two lines intersect. We maintain a deck, and this is how we insert lines. So we receive some information, which is the slope and the y-intercept, and we say that while the size of the deck is greater than 1, obviously because we have to compare this new line with the last line in the deck, so we don't want our deck to be empty. And now this is the part where you check if the intersection of this new line with the last line is less than the intersection of the last line with the second last line. So that's just checking if the last line has a x value, intersection x value greater than this the new intersect value of the new line with the last line. Then we basically remove the last line like I showed you. Now in the end, we should perform this deck empty check, and this is because initially when our deck doesn't have any lines, then we can't really access anything at the back of the deck. So we insert a new line and we say that it becomes useful from the x coordinate 0. Since all our queries are positive, we won't have any negative x value queries, so this will work. And then in the end, after these, so if it's empty, then we just return and we don't reach here. But if we do reach here, we just insert this new line, and the point at which it becomes useful is its intersection with the last line in the deck. Let's look at a query function. So this is what I basically told you, when the size of the deck is greater than 1, we again want that so that if it doesn't become empty. And we'll basically look at the front of the deck now, and we say we look at the first element, zero based indexing here. So we look at the element with index 1 and we check is the point at which it becomes useful less than or equal to the query value. Now if this is the case and this is the second element in a deck, that means we should remove the first element, because if because all of these intersection points are maintained in ascending order, and if the second element of the deck has an intersection point less than our query value, it means that the first line in our deck is also less than it. So we simply just pop the first line from the deck. But if we have a case when this is not true, Then we just break, and now the first line in our deck after this is done, it's the optimal line. So we evaluate the answer for that line and we simply return that. So this was for case 1. Now what we do when we have case 2? When we want to query for case 2, we actually can't remove any lines since our query values aren't monotonic. So here we just binary search, and you simply just, the idea is to binary search. It'll depend on the syntax of your language. This is just a fancy way of writing this in C++ with lambda, and then you again return the value, the y value you get with that line. And the rest of it is basically what I showed you in the starting of the video, how we changed the recurrence into the equation of y is equal to mx plus c here. So we maintain this DP array. We're at the first node, so 0 based indexing again. DP of 0 is equal to 0. Since there is no cost reached there, we already at it. And now, okay, so let's see how you insert new lines. So when we want to query, we give it our x value. Let me just go back to the slide, the page. Okay, so query and adding a line. Let's first look at adding a line. So basically when we need to add a line, we need to give its y-intercept and its slope. And as we saw, the slope is minus 2 into h of I, and the y-intercept is h of I square plus dp of I. And since it has dp of I, which means that we'll be calculating dp of I before actually inserting the line. And what about querying for a line? So this was addition, and so when we add it, we just say add, the slope is this and the y-intercept is that. Now when we query, we say that dp of I is equal to query, and what was the query value? It was basically x, which is h of I. This is the slope. So we query for h of I. Now if you remember, we still have to add these terms to the answer. So plus h of j square, and this is querying and this is addition, and this is what the code does. So since initially we don't have any cost, we simply add that line. So this is the slope and this is the y-intercept. Now for every I greater than 0, we query, we add a constant cost to it, and we insert that line. In the end, dp of n minus 1, 0 based indexing stores our answer. So the total time complexity for this was O of n, which is linear time, and this was possible because our slopes were monotonic and our query values were also monotonic. If the slopes weren't monotonic or query values weren't monotonic at all, we could use some data structure and do it in n log n, because for each element we had to query once, and querying and inserting with some data structure would take log n time. Again, I'm not going to explain those data structures here, so I'll leave some links down in the description. And when our slopes are monotonic but our query values aren't, again it'll be n into log n, because We'll be binary searching for every query value since we can't be deleting lines from the front of the deck. That was it for this video, guys. Thank you for watching. If you want to learn something, please let me know in the comments below, and I'd appreciate your feedback on how this video was.